Let me just introduce our tutorial for the next session here. So we have Toby Brown and Stephen Gwyn presenting a tutorial on using CANFAR and YouCat. Toby Brown is the Plaskett Fellow at Herzberg Astronomy and Astrophysics Research Center in Victoria, British Columbia. His main research focuses on the evolution of galaxies and the formation of stars. And he's a member of the ARCADE Science Platform Working Group at the Research Center. Prior to this, he was a co-PI of the ALMA development study, which funded much of ARCADE's software development. Stephen Gwyn works as a data specialist and science coordinator at the CADC. His specialty is data pipelines that handle data from MegaCam on CFHD. This has led to producing large source catalogs, which in turn has led to distributing large catalogs. So we're going to have a tutorial about CANFAR and YouCat from Toby and Stephen. Yeah, go ahead. Thank you.
Perfect. Thank you. And thanks for the introduction. I will just mention that after sort of weeks of inactivity, the builders have chosen this morning to turn up and taken to their task with relish. So I apologize if you hear banging and clattering from the floor below. I would also like to say thanks to Chris for that really excellent talk. I'm a bit of a notebook evangelist, and so it's really encouraging to hear the progress on how to share that and yeah, use notebooks to their full potential, I think. Okay, so yes, as was mentioned in the introduction, I'm the Plaskett Fellow at NRC. I've led various aspects of this project, but most importantly, I'm a user of ARCADE, which is the CANFAR science platform. So just to sort of put us all on the same page, when I say ARCADE in this talk, what I'm talking about is CANFAR's secure, stable, scalable, cloud-based science platform on which users can access, process, analyze, visualize data, and so on. So in terms of motivation as to why do we need science platforms, why is much of the community transitioning to the cloud, and so on, well, I tried to have a little think about the different barriers that astronomers are increasingly facing in their research as things like data rates and data sizes, computational requirements increase. And so the obvious one, and the one I'm sure pretty much everyone has run into here with their local machine, is storage capacity. So you know, across the wavelength range with theoretical hydrodynamical simulations and so on, the storage capacity needed for the data is just far outstripping what is available on even kind of the latest and greatest local machines. We just don't have the kind of resources required to deal with these terabyte scale data sets very efficiently. The next one, in a very related way, is the same kind of the other angle on the same problem, which is compute capacity. You can hit the kind of the limit of what you're able to do with your local machine and its memory and so on pretty quickly. And then one of the important ones that sits at the core of this meeting is reproducibility. So software and computing environments, methodologies, even data itself is just becoming increasingly complex and fragmented. And so, for example, I work with ALMA data primarily, and the complexity of the software and the data sets means that two people can download the same data from the archive, perform a kind of similar reduction, and not get exactly the same answer. So this is a problem with reproducibility of science. Yeah, as we sort of add in the features and increase the scope of what our software stacks are capable of doing, they obviously increase in complexity. And in particular, right now, a lot of the onus is on astronomers, on the end user, to install and manage various versions and dependencies, value-added software packages, different publicly available codes, and so on. And the integration between those different software suites and the interoperability of that software is virtually non-existent and can change from computing environment to computing environment. And then the kind of final barrier that I was thinking about putting this talk together is essentially the globalization of astronomy. So you have really distributed data and teams. So data is physically stored in different locations all over the world, and the teams are located everywhere, right? So trying to unify that into a shared analysis or methodology is quite difficult. Even just the basic problem of how do I move this large data set from A to B is also a non-trivial challenge. So that the net result of all these is to stymie collaboration and science in general. I think that there's a risk actually that astronomers end up becoming their own sort of part-time sysadmin, or even having to pay university sysadmins to manage their local systems. And obviously all of this puts a big demand on both time and finances for a given astronomer. And so wherever you have those sorts of demands, you also introduce an equity issue. So, you know, better resourced astronomers at perhaps more larger institutions may face less of these issues or fewer of these issues than younger astronomers, for example, and astronomers coming through. So that's also something that science platforms are starting to hope to address. What I'm aiming for by the end of the demo is really to convince you that science platforms in general, not necessarily just Arcade, but science platforms in general can help overcome these. Okay, so let's move on to Arcade, which is this our cloud-based science platform that we have out here. So this, from a user point of view, is essentially what Arcade looks like. And I don't want you to sort of absorb all this at once. We can step through and just focus on the individual components. So first off, like many cloud systems, we have this shared scalable storage. And what this allows is for teams to have very large, but crucially shared project directories, so that you know, when the data goes into the system, it's then the same data that's shared throughout the team. We also have scalable compute resources. So you just request the resources that you need for your project. If for one project, you decide, okay, I need more, say, memory, well, you just go back to the well and you ask for more memory and ramp it up and so on. So you can scale up and scale down crucially, and that allows for really efficient use of resources. On the more technical side, this is all handled using Kubernetes, which, so my understanding is that this is now becoming industry standard for managing the deployment, the scaling of what is containerized software, basically. Okay, so on this containerized software, in addition to the standard software suite that you would expect when you log into a science platform, things like Jupyter and visualization tools and so on. One of the key aspects of Arcade is that it gives its users the flexibility to build their own computing environment through what are called software containers. A software container is just basically packaged up software so that all the dependencies are there and it can be deployed on a given system. Now, what this enables is the possibility of just integrating your own analysis tools or your teams or your community's analysis tools into your version of Arcade, into your science platform. And it's almost infinitely customizable. So just to give you one example, I'm at least in part a radio astronomer, and in radio astronomy, we use a specific software reduction suite data reduction software suite called CASA. And so what I did is I packaged up CASA and I deploy it on Arcade. There's a little bit of technical know-how on how to do it, but it's fairly straightforward. And then all my CASA commands and so on are available for me to use within Arcade. They're also available to anyone who wants to use that container and that particular image. And I will show an example of that shortly. Okay, the fact that we base the science platform on this containerized model, it really facilitates reproducibility, because you can just share the script that builds the container. You can post that to GitHub. You can even deploy it on sites that build and share containers like Binder, to be deployed by others, to be modified, to be edited. If you so want, you've got all version control that comes with Git and so on. So you can do things like saving the exact version of the software and the dependencies for the computing environment, and then the reduction and the analysis that you completed. So, I mean, providing you are diligent as a user, you are capable of exactly reproducing the analysis that you've done, because it's the same software and the same data. And then integration is improving, but like I mentioned, we are trying to integrate a little bit with both GitHub and Binder on this front. Okay, so and then the other thing that the shared storage allows for the user is this the preloaded data sets, or kind of contributed data sets by teams. So just to give you an example, I'm the PI of an Alma Large program, and all that data sit in a project directory on Arcade that anyone who's part of this Alma collaboration is capable of accessing. So they can log in, and then all the raw data are there, the reduced data, the data products, and they can just plug that straight in at any stage they want to in their analysis, and away they go. And they're always looking at whichever version they want in terms of the data. Its versions. So, okay, and finally, it can sound a little boring, but user authorization and authentication. So how CANFAR manages its user sign-on is via a single sign-on for all the CANFAR services. So Arcade is just one of the CANFAR services. You also have cloud-based storage. You have YouCat table publication that Stephen will talk about in the next demo. We have virtual machines, and then the science platform, and all this is managed by the same single sign-on. And crucially, there's also group permissions that you as a user are able to edit. So I can manage my collaborations access to all my data, to if they want VMs, if they want access to the science platform, if they want to publish tables. All of this, yeah, it is managed through this user authorization and authentication. Okay, so this taken as a whole is how Arcade looks like to a user schematically, but I'm going to sort of do something that is potentially quite unwise, which is try and sort of give you a demo of some data reduction on the Arcade platform, sort of live. So please tell me if it hasn't changed screen. You should be seeing canfar.net/science portal. Okay, so here I'm logged in. This is my single sign-on. I'm logged in to the science portal that's on the website, and I want to fire up a session on Arcade, the science platform. So I just click the plus. The session type I want is notebook, which is actually Jupyter Lab is what we're going to be firing up. And the image I want to start is this CASA 6.4. You see there's a whole list of images here that users have contributed, whether that's got some JWST, LSST, some machine learning software and so on. But the one that I want to focus on now is CASA. And just remember, CASA is this kind of radio astronomy data reduction package. So we load up the correct container image, let's call this ROSA 2022. And then in terms of memory, we can go right up to 190 gigabytes of RAM. I don't want to sort of be a resource hog, so let's just drop that to 16. Number of cores at the moment, we cap it at 16. But I'm just going to select 2 for the purposes of the demo. And then we launch. And it usually takes sort of 30 seconds or so to fire up, maybe a minute, just because what it's doing is building that container and sending it. So I'm piping it through to you. All right. So now on your screen, you should be switching across to the Jupyter Lab view that is firing up. And if we're lucky, boom, everything is coming up as it should. So here I just have a very basic ALMA data reduction demo. Okay, I'm landed in my home directory here. Don't judge me, it's not the tidiest. I created this ROSA 2022 folder, and here is my IPython notebook. So let's just fire up a terminal as well. I hope most of you are pretty much familiar with Jupyter Lab. If not, I would recommend it. And so what I'm going to do here is, rather than sort of plug you through a data reduction that you don't really care about, I just want you to take note of certain things. So for example, we are downloading this data direct to Arcade, and at no point in any of this process will we ever touch the local machine. So there's no sort of onus on me to have some high storage capacity or good compute resources on my local machine. Once this has finished downloading, we can import all the tasks we run, and I will just allow this to run, and hopefully it should execute no problem. Of course, it's now taking longer than I would expect. But the point with this cell that I want to show you is these CASA tasks are all preloaded into this particular container image. If you had loaded one of the other containers, you would not see this, and that's because I contributed this software to this container. Okay, so here's just printing out some meta information of the data. And now we're running the data reduction task. And of course, you have a good record, if not a totally permanent record, of the command you used on your data reduction task when running in this way. Now, one of the key points, you can see here that my ALMA data reduction script is in my home directory. But I'm not dealing with the data in that directory. And that's because how Arcade is set up, we have home directories and project directories. And so what I've actually done is created a project directory that I will use for my data reduction and storage in this way. And I've just called it ROSA 2022. We have data, and here you see I'm pointing to these directories. The key here is that I'm the one who has access to my home directory, okay? But my team have access to the project directory. And so this is the shared file system. And so now if I say to my collaborator, okay, my ALMA image.fits is saved in this directory, they can go and view it, they can continue this analysis, they can go check whatever they want out with the data. The same would be done for shared scripts. You would place them in this directory here. Okay, so what else did I want to show? Here we just have some basic, an image done with matplotlib, but say I want to do a bit more of an interactive visualization of this image. Well, we actually have deployed CARTA, which is a visualization tool, on the Science platform. Now, I'd already fired it up because I didn't want to go through the palaver of loading it up, but it doesn't take long. And it's done in a very similar way to how I started the notebook. So we can now start CARTA. And what you can see is we've landed straight in this projects directory. You see ROSA 2022. This is all exactly the same file system. And now we have my Alma image that I want to do some interactive visualization on. So I don't know, maybe I want to change the scaling or do however you want to deal with your data. CARTA is a fantastic tool for checking it out. Oh yes, and one thing I just wanted to know is say, all right, let's say I found my kind of Nobel Prize winning thing. I've discovered whatever it is you want to discover. I can get really excited about that, and because it's CARTA, I can just export an image to my local machine straight away, and that just sends essentially a screenshot of this image here, and I can ping that off over Slack to my collaborators. Because of its JupyterLab, you can come at it a different way, and you can like download, right click, download. That will save my Alma image to your downloads and so on, and you can fire that around. So you have all the bells and whistles that come with tools like JupyterLab or CARTA integrated fully into Arcade. Okay, so working in this is my preferred method of working, but not every workflow allows you to work in this way. There are some desktop applications, for example, or more legacy software that require a desktop Linux environment. So CASA is actually a good example of this. Older versions of CASA can't be run in the notebook in this way. So what we also provide is a desktop environment that is just basically Linux. And you can see here, I've just loaded some examples of user contributed software that runs on the desktop environment. Much of this will be familiar to many of you. So for example, DS9, TopCat is a table manager that runs on the desktop. Here is an old version, or it's actually the same version, but just the desktop application for CASA. We have the logger for doing Alma reduction and so on that runs on the desktop. So this is just, again, the point I want to make here is that it's extremely flexible in how we don't make a judgment on how you want to do your workflow, and nor do we try not to constrain you. We want you to be able to perform the workflow you need to perform as a user. And then, of course, all of this desktop is just pointed to exactly the same file system. So if I wanted to open up my FITS file I just made in my notebook in DS9, because that's my preference, fine, you can. Okay, the final integration I wanted to mention is that CANFAR provides a web-based GUI for interacting with both its kind of static cloud storage for kind of more archival stuff, and also for Arcade. So what I can do, if it's your kind of preference, is to go to this website. So, I mean, you can access this from the homepage in CANFAR, and I can come through to this now is looking at the file storage system on Arcade. There is, if I refresh, there is the figure that I just made sort of a few minutes ago, and I can open it up and see it here. And of course, all my other files and scripts and so on are all accessible through this web-based GUI. The last thing I wanted to show you on that is this is going to be a little bit of live coding. I apologize, a little bit of live bash. So let's go through to projects and say, all right, I've done my full data release. Sorry, I've done my full data reduction. I want to release it either to the team, to collaborators, to the wider public. I want to just work completely publicly. So what I can do is go and use VCP, which is these are CANFARs. It's like CP, but VCP, because you're copying between storage systems. and I can take my fits image and just send it to VO space. So TH Brown is my VO space, Rosa 2022. It's copying, and now that's sent. And so if we go to CANFAR, of course, sorry. TH Brown, and then Rosa 2022, you see it's here. And this is public now because I said it as public prior, but this is now, I could share with you this link, send it around, and you have a public data release. You can give it your DOI for your various service or however you want to do it. So what the point I'm trying to get across is we've just essentially gone from archive through analysis to data reduction and analysis to data release without ever touching your local machine with a customizable software suite, which is CASA. Okay, in terms of that customizable software suite, it's really straightforward. There are software containers, and for those of you in the know, you use things like Docker files to build them. So here is just an example on GitHub of this is a desktop application that runs CASA. Actually, the version I was just showing you. Okay, so let's go back to the slides. I am more than happy to take questions if people have them, but I'm not sure exactly how best to manage that. Okay, so back to the slides. So I want to just stress this, the power of these customizable software and the containerized applications. I'm really a big advocate for it. And the reason is this, like you have your traditional use case of all your different astronomers using potentially even the same software packages or different versions of the same software. And they have to manage and look after that themselves and go and look after that themselves. But for Arcade, what that allows you to do is essentially within your collaboration or even just within your community, you have one person contributes your software container image to the platform, and then you've essentially built a shared computing environment that your community can use. So I think this is a really powerful application of Arcade, and I see that I'm right at time. So I'm actually going to just pop this slide up and take questions. So apologies for running over.
Thanks very much. Okay, so we do have one question, I think. It was by Peter Shiklona. He was saying, so Arcade looks great for small or moderate jobs, but how does it handle long-running jobs? And are there alternatives if we need many cores, for example, for distributed computing for bigger problems?
Yes. So I'm not 100% on the technical side, so I don't know what the upper limit on the number of cores is. But the limits we placed in there they're artificial. They're set so that we don't have sort of people coming in and just hoovering up all the resources all the time. And so it's kind of more flexible than than just the web UI will sort of indicate there. The other thing we don't have now, but are working on and is a really top priority is batch mode. Batch for notebooks, actually. So yeah, the idea is you would set up your notebook process and then you could run that in batch. And I think that would be really powerful for the bigger jobs.
I'll just add that, yeah, we already sort of have a Mickey Mouse version of it running, except that there's no user fairness setup. So that in principle, you could take over all the cores by running things in a sort of headless mode. And luckily, it's so hard to use that no one has actually cause this problem yet, but we are looking to make it easier and make sure that resources are properly distributed to the right users.
Excellent, thank you. Since we have no more questions, let's go ahead with Stephen's talk.
All righty. Share screen. Oh, yes. Yep. Can you see those slides?
Yeah.
Great. Oh, no. Slideshow. There we go. Okay, so changing. Okay, I can't see. There we go. Okay, so changing tack slightly. I'm going to talk about publishing user databases using the CDC system YouCat. So so the problem we're trying to solve here is sharing databases. There's a lot of ways to share files in astronomy. I mean, there's sort of generic ones like Amazon, Dropbox, or your people have departmental cloud storage systems, and these are all fine. And then there's another set of tools that are sort of specific to astronomy, like VOSpace, which are better because they're aware of the kind of software we use, like FITS things. And so the problem of sharing files in astronomy is basically a solved one, and it's just a question of how big one can make them. It's somewhat harder to share database tables. So you can share the whole file, but if it's a really big table that you've created, that's not sort of really scalable. People have to download the whole thing, or maybe they're only interested in one little part of it. And so consequently, it's far better to use TAP. So TAP stands for Table Access Protocol. It's probably been talked about a little bit in this meeting. It's an International Virtual Observatory Alliance standard. It's widely adopted, so not all the IVOA standards get picked up by actual users, but TAP really has taken off, and almost all the TAP services are compliant, which again is not always the case with all VO services. Some of them are kind of compliant, some of them are not. Whereas TAP really has got traction from the community. It's a web service, so the root URL for each service changes. So ours obviously have CADC in the name, and the content changes obviously from place to place. But the method and the syntax are identical, so that if you know how to use one of these services, you know how to use all of them. All you have to change is the root URL and figure out which tables you're trying to query. TAP uses the astronomical data query language, which is yet another variant of SQL. But the advantage of ADQL is that it's standard from all services, so that all the TAP services agree that they're going to use this particular flavor of SQL. So you don't have to, argue about whether it's top 10 versus limit 10 or what have you. All the various different SQL dialects. It's just one dialect, and everybody's just agreed on it, and everybody will modify their services such that works. In addition, it has astronomy specific features, so that there's not just the standard integers and floats and strings and whatnot. There's also positional data types, so that you can define something as being a position, or a circle, or a polygon, or a rectangle, or one of these other sort of geometric data types. The table access protocols, there's many ways to interact with it. So you can either go to a web page, and then you don't actually know that TAP's happening underneath. But the web page, it sends your queries off to a TAP service and sends them back to the screen. And this is just sort of like a standard, web query tool. But it also supports sort of low-level curl or wget commands directly to the service. There are various command line clients that exist. The CDC has one, but I'm sure there are others. The most popular way of interacting with TAP services is actually TopCat, the sort of well-known graphing program from the UK. And then you can also interact with it directly with Python scripts. So the little code snippet on the right there shows an example of a query that you could generate with just a few lines of Python and get the results back as a Python data set. So publishing a database via TAP can be cumbersome. So there's a lot of TAP services, but they're mostly sort of institutional and the reason for that is you need to set up a database. You need to set up a web interface to that database. You need to make sure it's compliant with the TAP standard. You optionally, or we really should register the service with the IBOA, and you do need to maintain all those things. You can't just sort of, things need to keep running. So you need to, and then optionally, you need to administer access control so that if you're not publishing a table to the public, to the whole astronomical community, you're actually just trying to do it for part of an internal release to a team, you need to administer access control. All of these things mean that it's a little bit of a schmozzle if you're just one team or one astronomer who wants to create and distribute a database table with good querying capabilities. So that brings us to YouCat, which is user-driven TAP services. So YouCat is your catalogs. We built it at the CDC starting in 2018. And it was sort of a response to, we kept on getting people who want to release their databases, and the interface to our TAP service, if a user wanted to distribute their table, the interface basically looked like send an email to Stephen Gwyn. And so Stephen Gwyn was getting a bit tired of this and thought it'd be better to change the control of the content to the user. And that has proved to be fairly useful, and certainly takes work off my hands, but more importantly, it puts control into the hands of the users. So the CDC takes care of administering the database. We take care of the web service. We take care of IBOA compliance, and the user takes care of the database content and specifies, using the same mechanism that Toby was talking about earlier, takes control of who actually has access to different parts of YouCat. So to publish a database, you need a CDC account, you need YouCat allocation and permissions, and that's all done very manually. It's not like you click on a link and you now automatically have YouCat allocation. You send us an email, it's a proposal, but it's not a particularly onerous one, because in astronomy, everybody tends to know who everybody else is. And so we generally do these allocations on the basis of a 2 or 3 sentences, a paragraph email that is sent in to us. And then we've never turned anybody away yet at this point. Ostensibly, this is only available to Canadian astronomers because it's running on Canadian government hardware. However, in practice, we extend that to people who collaborate with Canadians, which is, as it turns out, pretty much the entire world. So you also need to have a table that you want to publish and the means to transform it into various formats for reasons that I will explain in a few minutes. And you need to have some SQL knowledge, not a whole ton, but you need to have some SQL ability. So I think I've given a bunch of reasons why you should use YouCat. I'm going to give briefly a few reasons why you might want to not use YouCat. And the first is the current generic query user interface is ugly and low powered. It's not quite as cool as some of the better TAP interfaces that have been built out there. And that's just for the website. All the Python stuff and the wget and all the rest of all those access points are same as everybody else's, and you can access by TopCat or et cetera, et cetera, et cetera. It's only the CDC's web interface that is not as attractive as it could be. That said, have been talking to the folks at LSST who have a lovely tap interface, and we're hoping to borrow it. And when I say borrow, I actually mean steal. We're not going to give it back. The other reason why you might not want to use YouCat is designed to be sort of write once or a couple of times, update, but not it's not well suited to frequent dynamic updates. If you're using it as part of your processing methodology, that is not YouCat's probably not well suited to you. And then the table creation methodology, which I'm going to go through in a few minutes, sort of lacks polish. It works, it's high performance, but the way you actually do things is slightly clunky, I think. Okay, so I'm just going to walk through how one would do this. The first part is the sort of the step 0 is the setup. Is you ask for a YouCat allocation and have a schema created for you. So schema, being the equivalent of a directory. And then once you get that, you have to download and install the CDC tap client, but it's a Python package that installs with pip, so that's relatively straightforward. And then you need to get the tables ready. And then for each table, you need 2 versions. You need a header table in a VO table format. And this is just the header of the table, not the actual rows. And then as much metadata as you can include. So on the right there, you can see an example of a table. And, so you have a description of the table. You have the description of, here's a name of a column, here's the data type, and then here's the description of it. And then this next thing is actually a pause. Oops, didn't mean to do that. The name is pause for position, and it's actually not, it's not the ARIAN deck, it's both together stored as a dot in on a sphere. And then sort of more standard things like ARIAN deck and magnitudes and magnitude errors. Now that's for the table creation. For the table loading, you actually need another table that is in a different format. So either TSV, tab setter values, comma setter values, or good old PITS tables. So, yeah. Okay, I think at this point, I'm going to, as Toby said, going to go crazy and try and actually do a live demo of this. And I'm actually going to do it in the same environment that Toby was talking about. So can people see my screen now? Yes, no?
Yes. Yes.
Great. Okay. So this is on an arcade desktop, and you can see an X term and behind it an editing window. And I'm just going to walk through the steps of creating a table. A cool demo. Where is it? Oh, maybe I'm not, because I'm. Okay, have a sec. The one thing that's slightly clunky about the never, ever try to demo stuff. There we go. So here's my little script. So the first step is to get a certificate, which is the thing that allows, that defines you as you, and that the fact that you have permission. So CDC get cert, that's Gwyn, type in my password without displaying on the screen to 20 users. There we go. And it says I've created a certificate and it's stored in this particular file. And the next step is to create my cool table here. And so if I just do a header on there's that VO table I was talking about earlier. And I run this. And I have now it's already existed. So the first step, of course, is to delete the old version. So CBC, because of course I tested this before. Brilliant. And I have to type in the full yes, so I don't do this accidentally. So now, if I create a table, it's created, and if I list the schema of that schema, I see that I have created my cool table. And then if I list, look at the schema of that particular table, I can see that I have created something with columns and that everything is there, and that nobody can read it except me. So it's others read, false, group read, group write, nobody. So now if I wanted to create indexes to speed up searches, the first thing I'm going to do is create an index on a unique index on the ID so that I can't accidentally overwrite 2 rows. And then that's that. And then if I look at do a schema listing again, I can see that this is indexed. I can do a this is extremely powerful, not particularly sexy because it's just, you're just looking at the text that I'm typing, but I've now indexed the position. And what that means is that if I've had a huge table with many things covered the whole sky, positional search queries would now be very, very fast. It wouldn't have to go through each one to check. So now I have a table with actually nothing in it. So if I was to do a query on that table, I get nothing back. And now it's time to load stuff up. So this is, if I cat, that is all the rows that are in the table. And I can now load them up. And now if I do that same query again, I can see that there are, there we go, a bunch of rows. And I can also do queries where it's, there are constraints and so on. So that's sort of fairly standard. And then the thing that is cool about this is I can control who has access to this table. So as I said before, by default, when a table is created, only others cannot read, only you. But now suppose I want to share it with a few of my closest friends, I can do this, which changes the permissions. And then this now says that live demo sucks, sorry. That a group of people can read the contents of that table. But if I can now change that completely to have that. Ooh, that didn't work. Okay, well, that should have worked, and that what that should have done is given worldwide permission to everybody to read that table. So at this point, I think I've gone through the demo, and I think I've said all that I wanted to say. So I'm going to stop sharing the screen and take questions.
Thanks a lot. So I think we already have one. Yes. Could you tell us about the VOSA table format?
I cannot, because I don't actually know what it is. It's a mild change of VO table. But I can't. It's something to do with. I'm not a VO person necessarily. I'm a user, but not a person who argues. I don't know what the difference between quasi and VOS.
Okay.
VOTS are, I'm afraid.
So yeah, because we tried looking it up, and of course, there are very few, very few
Yes,
search results on it as well. Is
I use
that
VOT
part of the? Sorry, is that part of the IVOA documentation as well?
I believe so. Yes. Yeah. To me, it's just a distraction from PO tables, really.
Okay. Do we have any other questions? Okay. If not, then please continue the conversation on Slack, and let's thank all the speakers for the session and the speakers for the day as well. Thank you very much.